In the second part of section 5.4, we're going to look at part 2 of the fundamental theorem of calculus, and that's really what we did in section 5.3 when we evaluated integrals manually. So basically it says if we have an integral from a to b of some function f of x, it's going to be equal to the antiderivative, which is capital F, evaluated at the upper limit, minus the antiderivative evaluated at the lower limit. So let's take a look at an example. So in this particular example, we have the graph of f prime, which is the derivative of f is shown. We are given a value for f of 0, and we're asked to find a value for the function at 1. Okay, so we're going to utilize the fundamental theorem calculus in a unique way. So we're going to do the integral of f prime, and I'm going to be going from 0 to 1. Those are my x values that I'm asked to evaluate the function at. Or I'm asked to do at 1. I'm given the value of the function at 0. So the integral of f prime from 0 to 1, well, the antiderivative of f prime is going to be f evaluated at the upper limit minus f evaluated at the lower limit. Now we have three things in this equation. This I can get from the graph. This is given to me, and I can solve for f of 1. So this part right here is just the area under the graph from 0 to 1. So this is going to equal 1/2. My base is 1 and my height is 6. F of 1 is what I'm looking for, and f of 0 is equal to 5. So if I work this out, the left side is 3 is equal to f of 1 minus 5. And if I add the 5 over, I get f of 1 equaling 8. So my answer would be D. So a hint when the fundamental theorem of calculus may be needed is when they give you the graph of a derivative, and it's a shape that you can calculate the area of geometrically, and they give you one known value of the function, and they want you to find another known value of the function. And we're going to see this pattern as we proceed through the examples today. So here we are in question 5 from the 2008 exam. We're given a piecewise function, and right away we see that we're given the graph of g prime. We're given a value g of 2 is equal to 5. And first of all, we're asked to find the x-coordinates of all points of inflection for the graph of g. Okay, so inflection points, we look at part A. Inflection points happen where the derivative, where the second derivative, is undefined, or the second derivative equals 0. And since this is the graph of g prime, the derivatives are the derivatives of g prime are undefined when x is 1. So right here, at x is 4, and at x is -1. But at -1, the slope on the left and the right doesn't change. They're both positive, so that's not an inflection point. So my first inflection point is going to be at x equals 1, and the rationale is simply g prime changes from increasing to decreasing. My second one is going to be at x equals 4, and that is where g prime changes from decreasing to increasing. Okay, part B is asking us to find the absolute maximum on the interval -3 to 7. Okay, so absolute maximums will either happen at the endpoints or where the derivative goes from positive to negative. And there's only one place where the derivative goes from positive to negative, and that is right here at x equals 2. So basically, I need to evaluate my function g, would be my justification, at the left endpoint of -3, at 2, and at the right endpoint of 7. So to figure out -3, I'm going to use my known value, and I'm going to use my x value of 2, and I'm going to say I have the integral from -3 to 2 of g prime is going to be the antiderivative of g prime is g evaluated at the upper limit minus g evaluated at the lower limit. Again, this part here on the left side of my equation I get from my graph, so that's the area under the curve from -3 to +2. So if I calculate that area, it's going to be the area of this triangle, which is negative, and the area of this triangle, which is positive. Okay, so the area of my negative triangle is going to be 1/2. The base is 2 and the height is 4, and it's going to be negative because it's below the x-axis. is equal to, oh, sorry, I'm not done that, just the negative part. And then I have to add to that the area of the blue triangle, which is going to be 1/2, the base is 3, and the height is 1. So this matches up to the left side of my equation. G of 2 is given to me as 5, and I can evaluate G of -3. So on the left-hand side here, I'm going to get -4 plus 3 over 2 equals 5 minus G of -3. And if we isolate and solve for G of -3, we end up getting 15 over 2 would be the final answer. So G of -3 is 15 over 2. G of 2 was given to us as 5. And now we want to find G of 7. Okay, and to find G of 7, we're going to have to use the fundamental theorem of calculus again. So the integral of G prime going from 2 to 7 would be G at 7 minus G at 2. So now we have to find the area under the curve from 2 to 7. So we go back to our graph. I'm going to have, I'll get rid of these guys. I'm going to have this area here from 2 to 6, which is going to be negative. And then I have this triangle here that's going to be positive. So the area is going to be -1/2, and it's negative because it's below the x-axis. The base of my red triangle is 4, and the height is 2. And my positive triangle is going to be 1/2, the base is 1, and the height is 1. G of 7 is what I'm looking for, and G of 2 is equal to 5. So now if I solve everything, okay, on the left-hand side here, I'm just going to get a new page. The left-hand side, I'm going to get -4 plus 1/2. And if I add the 5 over, that's going to end up being G of 7. And if I simplify this, I get G of 7 being 3 over 2. So G of 7 is 3 over 2. So now I can look at my table, and I have my largest value of 15 over 2 right here. And that is going to be when the x value is equal to -3. So we just write a statement. This is our justification here. So we're going to say I get an absolute max of 15 over 2 when x is equal to -3. All right. In the next question, part C, it says find the average rate of change. And the average rate of change from -3 to 7 of graph G. Okay, so to find the average rate of change of G, I'm going to have to use my average rate of change formula. So average rate of change is going to equal G of 7 minus G of -3 all over 7 minus -3. Well, G of 7 we found in part B to be 3 over 2. G of -3 was 15 over 2. And this is all over 7 minus -3, which is 10. So this ends up being -12 over 2, which would be -6 over 10. So the average rate of change is going to be -3 over 5. And it says find the average rate of change of G prime. And then it says, does this mean the mean value theorem applied on -3 to -7 guarantees the value C such that G double prime is equal to this average rate of change, why or why not? So to find the average rate of change of G prime, I'll just do it right here. So it's going to be G prime at 7 minus G prime at -3 over 7 minus -3. And G prime at 7, I just read that off the graph because this is the graph of G prime, is going to be 1 minus G prime of -3 is -4, and this is all over 10. This ends up being 5 over 10, which is 1/2. And does this mean the mean value theorem can apply to this? No, it doesn't, because G prime is not differentiable from on the closed interval -3 to 7. So therefore, a mean value theorem does not apply. Okay, so there's the 2008 question, okay? And now we're going to go on to our next example, which is very similar. Again, we're given a graph of f prime. We're given a value of the function at 1. And in part A, they're just asking us for a relative maximum. So for a relative maximum, we're looking at the interior points where the derivative changes from positive to negative. And we have 2 of those. So at x equals -3 and at positive 4. And what's my justification? Because that is where f prime changes from positive to negative. Part B, final intervals where the graph of f has an inflection point. Well, I have a slope of 0 right here, so f double prime is 0 there. It's 0 here. I have a cusp here with a change, g prime or f prime changes from increasing to decreasing. So those are my 3 candidates. So at x equals -4 and at x equals 2, f prime changes from increasing to decreasing. And at x equals -1, f prime changes from decreasing to increasing. Okay, for part C, they want us to find all intervals where the graph of f is concave up and has a positive slope. Okay, so a lot going on there. The graph of f is concave up, so that means the second derivative is positive and has a positive slope, and that means that the first derivative is positive. So for part C, I'll just put that, say, right here. Whoops, change colors. So for part C, if the graph is concave up, f prime has to be increasing and above the x-axis. So -5 to -4. The graph is increasing, so the second derivative is positive, and it's above the x-axis, so the first derivative is positive, and the second place it would be is from 1 to 2. And your justification is that is where f prime is increasing and f prime is greater than 0. Now in part D, they want us to find the absolute minimum value on the closed interval -5 to 5. Okay, well, the absolute minimum value is either going to happen at the endpoints or where the derivative changes from negative to positive, which is right here at f of 1. So I'm going to have to go through my table approach here. So I have x, and I have f of x, and my endpoints are -5 and 5, and my critical number is 1, and we already know that f of 1 is equal to 3. Okay, and to find f of -5, I'm going to do the integral from -5 to 1 of f prime, which is going to be f evaluated at 1 minus f evaluated at -5. Again, this I have given to me. Okay, this I can get from my graph, and I'm going to solve for f of -5. So the area under the curve from -1, or from -5 to 1 is going to be this semicircle, which is positive, minus this semicircle here, which is going to be negative. So it's going to be 1/2 pi, the radius of that first semicircle is 1, minus 1/2 pi, the radius of the second semicircle is 2, is equal to f of 1 is 3, minus f of -5. So doing the math here, I get pi over 2 minus 4 pi over 2 is equal to 3 minus f of -5. And if I solve for f of -5, we'll end up getting 3 plus 3 pi over 2. So that's f of -5. And to find the value of f of 5, I am going to do the fundamental theorem of calculus again. So this is function at 5 minus the function at 1. Again, this part here I get from my graph. So it's the area under the graph from 1 to 5, which is going to be a triangle. This triangle above the x-axis, subtract this little triangle below the x-axis. That's going to be 1/2. Base is 3, the height is 2 for the first triangle, minus 1/2, the base is 1, the height is 1 for the second triangle. This equals f of 5 minus f of 1 is 3. And if we solve for all of this, I'll just let you do the solving on your own, but f of 5 does work out to be 11/2. So therefore, the question is asking, what is the absolute minimum? Okay, well, it looks pretty clear that my absolute minimum occurs when x is equal to 1. So then you're going to write a final statement that the absolute min value equals 3 when x is equal to 1. And our justification is really the table here and all the work that we showed. Okay, I'm hoping these are making a little bit of sense. Okay, again, here's an exam question from 2013, and it shows the figure above shows f prime, the derivative of a twice differentiable function. It tells us the graph has horizontal tangent lines at 1, 3, and 5. And now it gives us the area of each of these regions. And they're also giving us a known value on the function that f of 8 is equal to 4. So right away, I should be cluing in the fundamental theorem of calculus is probably going to be used here somewhere, because I have the graph of f prime and they're giving me a value of the function, or a value on the function. So question A says find all x values on the open interval for which the function has a local min. Well, local min for part A is just going to be where the derivative changes from negative to positive, and there's only one place where that happens, and that's going to be right here at x equals 6. And the justification is going to be that is where f prime changes from positive to negative. Part B says determine the absolute minimum. So again, there's the absolute minimum on the closed intervals 0 to 8. So we want to do our table again. And again, when we do our table, we have to consider the endpoints. So again, I'm going to have my table here, x and f of x. I have an endpoint of 0 and an endpoint of 8. And my relative min is at x equals 6. So that's another candidate. So now I need to figure out all of these values. And I have a known value that f of 8 is given to be 4. So to find the first one, I'm going to do the integral from 0 to 8 of f prime. This is going to be f of 8 minus f of 0. We already know that f of 8 is 4. This is the area under the graph from 0 to 8. Now note in this question, they don't give us a geometric shape, but they tell us the area in all of these regions. So if I want to calculate the area from 0 to 8, it's going to be 2 plus 6 is 8. 8 minus 3 is 5. And 5 plus 7 is going to equal 12. So the area under my graph, so this part, of my equation is going to be 12 is equal to f of 8, which is 4, minus f of 0. And if you isolate for f of 0, you get f of 0 being negative 8. Now to figure out f of 6, it's going to be the integral from 6 to 8 of f prime, which is f of 8 minus f of 6. So this area from 6 to 8 is simply 7. F of 8 was given to us as 4 minus f of 6. And again, if I solve for f of 6 here, I'm going to get negative 3. So the absolute minimum occurs at when x is 0. And so therefore, my final statement is going to be my absolute min is at the point f of 0, and the min value is negative 8. Okay, so there is part B. Part C, on what open intervals is the graph both concave down and increasing? So concave down means that g or f prime is decreasing and above the x-axis, because f prime is also positive. So that means It's decreasing above the x-axis, so for that question, it's going to be from 0 to 1. So for part C, if you look at the graph from 0 to 1, union with 3 to 4, because that is where f prime is greater than 0, and f prime is decreasing. Now part D is a derivative question, and they're telling us the function g can be defined as f of x all cubed, and they're giving us f of 3 is negative 5 over 2, and they want us to find the slope of the tangent line to the graph of the function when x is equal to 3. So that means we want the derivative of g at 3. So again, we'll start with our function for g of x, and g of x is equal to my function all cubed. So the derivative, I have to use the chain rule. The 3 comes out front. F of x drops to a power of 2. And then I must multiply it by the derivative of the inside. And now I'm going to evaluate this when x is 3. Okay, well, f of 3, they give me that in the question as negative 5 over 2 squared. F prime of 3, I look at my graph, and at 3, f prime of 3 is 4. And now this works out to be 3 times 25 over 4 times 4, and this works out to be 75. Okay, another example, we're looking at the 2018 exam, okay, and in this question, we have a piecewise function again. They're telling us that it's a piecewise function from negative 5 to 3. It's a linear piecewise function, and then from 3 onwards, g of x is equal to 2 times x minus 4 squared. We know that f of 1 is equal to 3, and the question is asking us to find f of negative 5. Okay, so again, in part A, the fundamental theorem of calculus is going to apply. So I'm going to do the integral from negative 5 to 1 of g. And they're telling me that g is the derivative of f. So if I integrate g, I'm going to get f evaluated at 1 minus f at negative 5. And we know what f of 1 is. F of 1 is given to me as 3. So I can calculate this as the area, as the area under the curve. So I'm going to calculate the area under the curve from negative 5 to 1. So I am going to get a rectangle, a triangle, and a triangle up here. So the area under the graph is going to be, well, this is a 3 by 3 rectangle, so it's going to be negative 9. My triangle is going to be negative 1/2. The width is 1, and the base is 3. Plus the triangle above here is going to be 1/2, 1 times 2. So this equals the area under the curve, and that equals f of 1, which is 3, minus f of negative 5. So if I evaluate all of this and solve for f of negative 5, it's going to work out to be 25 over 2. So there's my answer for A. Now in part B, they're asking us to evaluate the integral from 1 to 6 of g of x. So basically, for part B, we're asked to evaluate the integral from 1 to 6 of g of x dx. But if we look at our graph, from 1 to 3, I have a square. And then from 3 to 6, it's the area under my function, which is 2 times x minus 4, all raised to the power of 2. So to do that, I have to break this up into 2 parts. So it's going to be integral from 1 to 3 of g of x dx, plus the integral from 3 to 6 of 2 times x minus 4 squared dx. And this part here from 1 to 3, we said was just a square, 2 by 2 square, so that's going to be 4. And to integrate this, we're going to learn u substitution a little bit later on, but because the derivative of the inside here is 1, I can just apply the power rule to this. So I can add 1 to the exponent. This becomes x to the 4 to the power of 3. And then I divide by the new exponent, and this is going from 3 to 6. So I have my 4 from my first part of my integral, and now I plug in my upper limit. And I'm going to factor the 2/3 out because it's a constant. So this is going to be 6 minus 4 squared minus 3 minus 4, sorry, cubed. And this is going to be 4 plus 2/3 times, this is going to be 8 minus -1. And if I work this all out, this works out to be 10. So again, in this question, we had to do an integral, part from the diagram and part from actually integrating. Okay, if we take a look at the next part, it says for the interval -5 to 6, on what open intervals, as any, is the graph both increasing and concave up? So we want to know where the graph of f, and this is f prime, which is really g, we want to know where it's both increasing and concave up, so we have to know where it is above the x-axis and increasing. So that for part C, it would be from 0 to 1 and from 4 to 6, and that is where f prime is greater than 0 and f prime is increasing. All right, and the last part, question D, says find the x-coordinate of each point of inflection on the graph. Justify your answer. So again, if we look at our graph here, we have possible candidates for inflection points where we have sharp corners and where the derivative is 0, because remember, this is the graph of f prime, and the only place where I have a sign change is going to be when x is equal to 4. So that's going to be an inflection point because f prime changes from decreasing to increasing. So there's a slope change on the other side of 4, but the other ones, it's a constant, so there's really no slope sign change because we have a slope of 0 on the either side of these other points here. So that's my only inflection point. Okay, we'll take a look at our last example, and then you're going to have some time to work on an assignment. And on this example, we're given again, a function defined as an integral, and we're asked to find g of 4, g prime of 4, and g double prime of 4. So in part A, to find g of 4, I'm just plugging 4 into my integral. So it's the area under the graph of f of t dt. From 0 to 4, note that this triangle and this triangle are going to cancel out. So I'm going to have a 1 by 2 rectangle and a triangle. So it's going to be 1 times 2, the area of that rectangle, plus 1/2, the base is 1, and the height is 2. So this is up being 2 plus 1, so that's going to be equal to 3. So for the second part, I'm asked to find g prime of 4, which is going to be the slope of the tangent at 4, which is the slope of this line. So that means that, oh, I should back up there. To find g prime of 4, I need to take, first of all, the derivative of g. The derivative of g is the derivative of this integral, which, because it's going from a constant to x, the x just drops in place of t. So this is really g prime. So g prime of 4, sorry, we can just read that off of the graph. G prime of 4, because this is the graph of g prime, it's equal to 0. Then for the next part, when I want to find g double prime at 4, that's going to be the slope of the tangent line on g prime at 4. So that's the slope of this line. So I'm going rise of 4 and a run of 2, and it's going downhill. So my slope is going to be -2. So my slope here is -2. So there's part A. Part B says, does G have a relative max, a relative min, or neither at x equals 1? Well, at x equals 1, G prime, or f, sorry, which is G prime, is changing from negative to positive. So when the derivative changes from negative to positive, that means that it is a relative min. So at x equals 1, we have a relative min because G prime changes from negative to positive. Okay, part C, I'm just going to leave part C for now. We'll study that when we get a little closer to the AP exam. So I just want to look at this last example and then we'll be done. So in this last example, again, we have the following. We have P of x is equal to the integral from 0 to x of f of t dt. And then part A, they want us to evaluate 0, 1, and 4 in P, and then part B, 5, 7, and 8. So eventually we're going to make a table of values, and we're going to be evaluating 0, 1, 4, 5, 7, and 8. So using the fundamental theorem of calculus, if I put 0 in, I'm going to get the integral from 0 to 0, which is 0. To evaluate the integral from 0 to 1 of f of t, that's going to be the area of this triangle, which is going to be 1/2 the base, which is 1, times the height of 4. So this is going to equal 2. At 4, I'm going to be finding the area of that triangle, of this triangle, and of this rectangle. Well, these two triangles are the same. So finding the area from 0 to 4, I'm going to have two triangles of 2 plus the area of the rectangle, which is 2 by 4, which is 8. So 8 and 4, this is going to be 12. Okay, at 5, I'm actually taking off this triangle and this triangle eliminate. So to find the integral from 0 to 5, it's going to be equal to, I should make that neater, f of t dt. It's going to be the area of my triangle, which we found to be 2. That's the area from 0 to 1, plus my 2 by 4 rectangle, which is 8. So this is going to be an area of 10. And then from, that's 7, this rectangle is going to really cancel out that rectangle. So for 7, the integral from 0 to 7 of f of t dt, I'm really only going to be left with this triangle, and that's from 0 to 1. And that's what we said was 2. And finally, f of 8, I have equal area above and as below, and that's going to be 0. So those are the calculations for A and B. So we did those together. Part C, at what value of t does P have a maximum value? Well, it looks at my graph. I have a maximum at 4. And notice my derivative does change from positive to negative at 4. Okay. Also, I did check the endpoints, but the endpoints were 0. So for part C, at t equals 4, we get a max value. That's an absolute max. Question D, on what intervals is P decreasing? So if I take the derivative of P, P prime is going to be the derivative of this integral, which is really f of x. So we want to know where P is decreasing. So P is decreasing when P prime is negative, and since this is the graph of f, it's really the graph of P prime. It's decreasing when P prime is below the x-axis. So it would be from 4 to 8, because that is where P prime is less than 0. Okay, in the last part of question number for B, they want us to sketch the graph, and I just want to sketch this graph for you. So we have this table of values, and we want to sketch the graph. And our x values are going from 0 to 8. And these are going 2, 4, 6, 8, 10, 12. So 12, 10, 6, 4, 2. Okay, so we know right away that at 0 it's 0. So we'll plot that point. At 1 it is 2. At 4 it was 12. At 5 it was down to 10. At 7 it was down to 2, and at 8 it was 0. Whoops, at 7 it was down to 2, and at 8 it was 0. Now, looking at the graph of the derivative, wherever the derivative is positive, it's increasing. So I know it's increasing from 0 to 4, and from 0 to 1 it's increasing in a concave up fashion. Then it's increasing at a constant, and then it's increasing in a concave down fashion to 4 at 3. So it's kind of tricky to sketch this one, but it's increasing in a concave up fashion. And then from 1 to 3, which is going to be somewhere up here, it's a constant. And then from 3 to 4, it's still increasing because the derivative is positive, but in a concave down fashion. And then from 4 to 5, it is decreasing in a concave down fashion. So from 4 to 5, it's increasing in a concave down fashion. And from 5 to 7, it's decreasing at a negative constant. And then, oops, I got that wrong. 7 is already on my graph. And then from 7 to 8, it is decreasing in a concave up fashion. So it's decreasing in a concave up fashion. And that's kind of the sketch of my function. Okay, so in the you will have an assignment from this section you'll get in class, so you can try that assignment. And if you have any questions, you can feel free to ask me.